Howdy everybody, happy Thursday. I want to cover a couple of announcements quickly first and then get into the content video for today. First of all, I republished the Transformer article submission tab from this past Monday, the 18th. So that article for review is now live, and the tab to post it. So you can go to that and post that, send that in. Let's see, what else? Seems like I had something else announcement-wise. We're going to do another lab tomorrow. Today will be some content day, and we'll do another lab tomorrow. So I wanted to talk a little bit briefly about yesterday's lab. Hopefully you all found the period, which has a symbol of a capital T, a scripted T, for a pendulum. This is in the end of your lab manual, is the square root of L over G. Whole thing is square rooted. So this is a constant and then L over G. So of the three variables that we measured yesterday, amplitude, length, and mass, length is the only one that should have affected the period of your pendulum. So you should have graphed period versus length, and then you're going to submit that on your lab report. Okay? So I will erase this and get into some stuff for the day today. Maybe I'll erase this. All right. In your reading, you've come across a couple things, and you'll get some more reading today. If I took a string and tied one end of it to a wall or a post or something like that and shook it up and down, I would get a pattern that would look something like this. This is called a mechanical wave. Okay? Well, there's some parts of this mechanical wave that I want to point out. Number one, there is a midline, like this, right down the middle. And from the midline to the top and the midline to the bottom is called the amplitude. These top parts are called crests, and the bottom parts are called troughs. T-R-O-U-G-H. Okay? Crests and troughs. From one crest to the next crest is how we measure the length of a wave, and that symbol is lambda. That's wavelength. Now, it doesn't have to be crest to crest. It could be trough to trough. It could be from this point to the next successive point where it crosses the midline. So it's the distance. The wavelength is the distance between two successive parts. Okay? A couple other equation things that you'll encounter that I want to just touch on. Yesterday we measured the period of the pendulum, and that is simply the time for one complete cycle. Another characteristic of a wave is the frequency, and that's the number of cycles per time. If that time is in seconds, like it was for us in the pendulum lab, then that would be measured. If it was cycles per second, we would call that a hertz. That's the unit for frequency if it's cycles per second. But some things like the sun rising, we wouldn't use seconds. We would do cycles per day or cycles per hour or something more appropriate. Okay? All right. Another equation that or relationship you're going to come across is the speed of a wave. The equation for it is frequency times wavelength. So frequency times wavelength is wave speed. That is a constant for that particular type of string. If that was a rope or a chain or whatever, it would have a different speed, but for that rope, that particular rope, it would have a constant wave speed. Okay, secondly, once in a while, if I'm taking this rope and vibrating it up and down, and if I tie this off on a wall or a post or something, it'll reflect itself back on itself and look like this. And when that happens, the frequency is just right where the incoming frequency and the reflected frequency are out of phase 180 degrees. They're just out of phase perfectly. When that happens, this is called a standing wave. Okay, a standing wave. Parts of a standing wave, this part right here, there's literally no movement in that standing wave. That part where there's no movement are called nodes. Think of no as in no movement. Okay? These parts here where there's maximum movement are called anti-nodes. Okay? So there's nodes and antinodes in a standing wave. Some examples of a standing wave. Oh, let's see. Some of the air column in a vibrating, like a Coke bottle. If you blow over the top of the Coke bottle, you're forming that air inside to form a standing wave. And you're actually hearing the top of the bottle is an antinode. That's why it sounds really loud when you get the frequency of the blowing of the air just right. Some other examples in an older model car, let's say this is the fender of the car like this, there would be a radio antenna, fairly long. And at just the right speed, this radio antenna will vibrate and form a standing wave. It doesn't happen a lot, but just it happens from time to time. You'll see things in nature that will form standing waves. Water waves, the surface of a lake, if it hits a barrier and bounces back and hits a barrier and bounces back, it's in a channel or something like that, can oftentimes form a standing wave. And when it does, sometimes these amplitudes get really big in these antinodes, and it can be dangerous and destructive. So to buildings or bridges or things of that nature. Okay, so those are some pretty important parts of a wave. Another concept that I want to talk about is a topic called the Doppler Effect. So imagine you have a little bug. Here's a bug right here. Can't draw, it's too small. A bug is just sitting on a little puddle of water. Whoa. I'm going to have to do that over again. That's not very good. A bug is sitting on a puddle of water, and it's making circles, circular pulses. Perfect circles, right? Even though mine aren't perfect. It's just jiggling up and down, sitting in the middle of this puddle, right? The frequency is constant. Well, all of a sudden the bug decides to start swimming this way, to the right. Well, what happens is the crests of these waves get bunched up in the middle, or on the right, I should say. They get bunched up here, and they get spread out over here, okay? It appears the frequency is higher over here and lower over here for these wave crests, but it's not. It's the same bug jiggling up and down at the same frequency. That's called the Doppler effect, when the appearance of the frequency appears to change due to the motion of the bug. Well, sometimes that bug starts swimming a little faster and faster. And when it swims faster than the waves that it's creating, the bug just pokes his nose up here. It creates a wave pattern that you are all very familiar with. If you're out on a boat this weekend, we call it a wake, but technically it's called a bow wave. And it's when the bug travels faster than the waves that it's creating. Okay? If that was not a bug but an airplane, then this is a three-dimensional cone that's trailing behind the cone, and we call that a shock wave, or better known as a sonic boom. Okay? So that happens when the source travels faster than the waves that it's creating. Like your boat, if your boat is traveling faster than the water waves that it's creating, it's going to form a wake. And it's what you use to go wakeboarding or surfing or whatever on behind your boat. Okay? Let's see. Lastly, there's a couple of terms you're going to come across. You're going to come across the term transverse wave. And you're going to come across the term longitudinal. Those are two types of mechanical waves. A transverse wave would be like this rope vibrating up and down like this, but the energy of the wave travels like this, right? So this energy traveled like so, but the string or the spring or the whatever just vibrated up and down. When they're perpendicular to each other, that's called a transverse wave. A water wave, our example down here, a water wave is a perfect example of a transverse wave. If you're out fishing and you cast your bobber out and it's sitting on the water and a boat comes by, that wake of that boat is going to cause that bobber to just go up and down, and the water is going to travel towards the shore. The bobber doesn't hop on it and travel all the way in. The bobber just bobs up and down. Longitudinal waves are sound waves. And you'll see example, I'm not going to, well, maybe I'll draw a quick one. Sound wave is made up of a bunch of air molecules that are really tightly packed and then spread out, and then really tightly packed and then spread out. That's called a longitudinal wave. These parts here are called compressions. And these parts here where they're really spread out are called rarefactions. And you'll see that in the crash course video today, I believe. So I know that's a lot, but I wanted to highlight a couple things that are in your textbook reading, in your worksheet that you're going to assign. Today's going to be kind of a work day, a content day, and then tomorrow we'll do another lab. Let's get your transformer article review. That's going in your homework assignment. So it's a 10-point homework check, basically. Your essay, your solar essay is due tomorrow. Double check that tab and make sure that tab is open. I believe it is. I've had a few submissions already, so that should be good. But your solar essay, your 5-paragraph essay, is due Friday by midnight. And I will come back with you tomorrow for a video on our second lab of the term. Hope you enjoyed the lab, something a little different to do. So, all right, have a good day, everybody.